Here's a fun little thing that I like to do. I like to take an object from Blender, unwrap it, and then render out the P-world and the beauty as a flat image. And then I like to take them into Fusion and start emitting particles of the position of where the object is in 3D space. We can do some really funky things like this crazy disintegration effect here. So let's just start in Blender. The first thing we're going to do is just lay down a monkey, and we're just going to use a good old Suzanne here. And I'm just going to create a smooth shaded version of her and apply a subdivision surface on her. Something that we need for this effect is to have unique UVs for this object. And the reason for that is that each one of these vertices are going to be assigned a position in world space, but mapped to a 2D plane. So let's just start with the first one. I'm just going to create a couple of lights so we get a beauty render. And I'm just going to put down a quick area light, set up the scene. We're going to render with cycles because we need a proper baking workflow for this. So let's just create a couple of lights. That looks pretty good to me. We are going to turn down the maximum number of samples. We don't need that much. That's good. Something that we need to do is enable transparency on our render. And then we're going to create a new image. This is going to be the image where the texture has been baked down to. So we'll just call it baked. It can be 1K. That's fine. Let's create a shader. And in this case, principal shader is fine. So let's see what happens once we bake this down to the image. And you need to make sure in the shader that you actually select the bake texture you want the render to bake down to. So let's just bake everything down. And here we have Suzanne baked down to a flat image. So let's just go ahead and save this down as an EXR. Now what we need to do is render out the world space position into the UV map. So let's change the bake type from combined down to position, hit bake again. And this is now an image where each one of the colors in RGB represents a position in 3D space. So inside of Fusion, I've loaded both of these images. We'll have the comp beauty, which is just the diffuse lighting, and then we have the P-world pass. And you can see if you normalize the range that it contains all of the positions. So the first thing we're going to do is put down a P image emitter and a P render node. Now let's have a look at these. The first thing we can see is that the beauty is quite dark. So let's just expose it up a little bit and have a look at what that looks like in 3D space. So I'm just going to enable the grid so we can see it. And what the P image emitter does, it creates a particle for every pixel in the image. So if you zoom in, you can start to see that each one of the pixels are turned into a point. So just for the sake of speed, I'm just going to lower the resolution, and I'm going to do that by changing the density parameters. I'm just going to link it to the X so that I have a single slider to control. And you can now see that you get a lower resolution. So the next step is to use the P world to change the position of each one of the particles at the first frame. So we're going to do that with our good old trusty P custom. The P custom is super flexible. It reminds me a little bit of the old Houdini points node that lets you manipulate attributes. And in a similar way, we're going to actually plug this one in right here and clean it up a little bit. And in the particle tab, we're going to change the position X, Y, and Z to read the P-world image. And then we can use that to plot the position of each one of the particles. And we can do that with a function called get. And there's a couple of parameters to it. You want to get the red channel from the first input, so get R1, and you want to get it from the bounds. And in order to read the position of the image back to the particles, you need to specify some coordinates. And we can use that by typing pxi, which will be the particle's x position on the first image input, and then we'll just need to offset it by 0.5, and we'll do the same thing for y. So pyi 1, and we'll offset it by 0.5. And that's it. Now we just need to copy and paste this and change the get R to B, sorry, to G for green, and then we'll do the same for B. And this might look correct, and it kind of is, except it's in the wrong orientation and the wrong scale. And we can compensate that because Blender's coordinate system is Z up, and we just need to flip it around. And we can do that with another custom tool here, not a P custom, but a regular custom. And what we can do is we can map this number in one slider, which is called N1. So we can type multiply by N1, and we'll do the same for red, green, and blue. That gives us a slider that we can control the scale. This is the same as just multiplying it with a gain, and we want it to set to 0.01. So now we have the correct scale, but we have the wrong orientation. And what we do is just flip the channels. So we'll say green and blue are flipped. And now we have it in the correct space. So now we have a 3D object made of particles that are coming out of Blender. So the first thing I'm going to do is just disable the grid so we can have a better look at the particles themselves. And I'm going to increase the amount again. And if I hit play now, you'll notice something interesting. It completely disappears. That's because for every frame, it tries to set the position based on this image. And that creates a weird feedback loop where the particle tends to collapse in on themselves. So the clever thing we need to do is actually on the P custom, we have to go to conditions. And we have to change the last slider on the edge here to the start of the lifespan of the particle so that the position is only set when the particles are born. So if we hit play now, it all looks fine. And now we can start adding some interesting effects. So for instance, on the P image emitter, I'm just going to change it to lock on the initial frame. And we can leave the lifespan to something like 100 frames is fine. If we now put down a P turbulence, for instance, we can create these really interesting disintegration effects. So let's have it so that it starts from the top and goes down. So let's change the strength of the particle turbulence, but I'm just going to gang these parameters together. So I'm going to up the strength and I'm turn down the density. The density is essentially the scale. So we'll have something that looks a bit more interesting like this. Let's put this inside a region so that whenever a particle is inside the region, the effect will take place. And I'm just going to use this when inside a region and it's a cube. I'm going to make it quite wide, so 5 by 5. And for the height, I'm just going to set it above Suzanne's head. And then I'm going to animate the height. So at frame 1001, it's going to be quite flat. And then on frame 1050, it's going to be covering pretty much all of Suzanne. So let's play back and have a look at this. That's pretty cool. Something I want to do is to publish the Y offset because I want to use this parameter on a couple of other nodes. So I'm just going to click this publish button. Now I want to tweak the parameters a little bit on the turbulence. I think the size is a little bit too big. I think that looks more interesting. Now let's have it so that when the particles are inside the box, it actually flows away a little bit. So we can put down another node called P directional force, and that creates gravity. So if we hit play now, it all just falls down. But what we can do is have the same region and just link it to the P turbulence. So we want to say when inside region, it's a cube. We'll make it quite wide, but for the height, we're actually going to connect it to turbulence height. And then on the Y offset, we're going to do the same. We're going to say connect to P turbulence Y offset. So now all the points are collapsing down as soon as they're inside of the cube. But if we change the direction to, instead of -90 to 90, that means the thing is going to float away. So I thought that was quite interesting. Let's do a couple of changes to it. Let's have it so that it only happens at the first, let's say 25% of the lifespan of the particles as they're born. So that means that some of them will float away for, a third of their lifespan. But what I do want to try and do now is the opposite. So after a certain while, let's say we actually don't need a directional force with a box. We need a P directional force that falls down, but we only want it to fall down after a certain age. Okay, that was quite subtle. So let's change it quite a bit. Let's change the direction to the -90 because that was set wrongly. And let's have it so that the condition is happening a little bit later. Okay, that's pretty cool. So the next thing is to put down a P bounce. And the P bounce lets particles collide with objects. In this case, I just want it to collide with a rectangle. The rectangle can be quite big, and I want it to be rotated 90 degrees. If I switch to the left side, it's easier to see where the ground plane should be. So let's have a look at what this does. Okay, so there's plenty of bouncing happening. So I don't want any elasticity happening. And I know the points are going to be sliding all over the place. So let's just take down the density and have a look at it, playing back a little bit quicker. Let's say I'm pretty happy with this. Now you can see the particles are sliding on the ground, and you can fix that by putting down a P friction. And that'll just create friction in the air. But what I don't want is the friction to be happening all over the place, because that you can see now the points are actually sort of floating and stopped in the air. That's because they have too much friction. But we want to limit the friction to where the ground plane is. So we'll just do the same thing. When it's inside a region, as a cube, make it really wide. Let's say 10 by 10, and it can be quite flat as well. We'll just switch to the left side and put it down to the ground plane where the collider is. So if we have a look at this now, so that looks more interesting. Now, in order to stop these points that are falling further away from the camera, like they are moving past the collision plane, you can either increase the subframe sampling, or you can just cheat it. And we're just going to cheat it. So I'm just going to put down a merge 3D node and an image plane. We're just going to leave the material white for now, but I want to turn it on 90 degrees, move it down, and scale it way up. So let's say it's 15. We can probably take it up a little bit just before they're intersecting with the particles. And let's change the material to be completely black. No specular highlights at all. So that kind of stops it. So let's create a camera and do an interesting render of this. So I'm going to put down a camera 3D, and I quite like the view that I already have. So I'm just going to say copy point of view to camera and put down a render 3D node. And let's increase the particle count. So this is the image, and this is the viewport render. So one interesting thing we can do with the 3D render, if you set it to the hardware renderer, you can enable an accumulation effect, which gives you 3D depth of field, and you can put the quality quite a high up. So let's go to the camera and change the focal plane, and we probably need to just change the framing a little bit because it looks a little bit weird. And that's pretty much the effect that I want to show. It's just how to take an image and use that as data to drive other things, in this case, the position of other points. And this forms the basis of how you want to emit particles from objects within Fusion if you want to control them by texture. And that's something for a different day. I hope you guys enjoyed, and remember to click like and subscribe and all that jazz, and I'll see you in the next video.